Today in this Algebra 1 lesson, we're going to be taking a look at what is a function and what are the main characteristics and vocabulary associated with functions in mathematics. Well, first we're going to begin with distinguishing between a relation and a function. So for openers, a relation is any pairing of input data to output data. So we have something that we start with, that's our input, and as we move forward, something occurs to it, it describes another event or phenomena that happens, and that is our output. So anytime we have these, we see a relation. Now a function is a special type of relation. A function is a relation that pairs any given input value with exactly one output value. Now by this, if I start with a data piece as an input, it has to lead me to something else. There can't be no data associated for an output. Also, if I start with an input value, I get only one output back. I can't have two or more, but I must remain with just that one. Now, on display here are several different types of relation data sets. We have simple lists of numbers. We have it as points. We have them put in as tables. And we have what's called a mapping diagram. And we're going to look at each of these and say, is this a valid function or is it just a relation? So when we see items put in as points, we have a starting and an ending. The first one, typically in math, we call this the x value, is our input value. So here we have -5 as an input, 0 as an input, 5, and 5. Now our outputs are the second values, the y. So 0, 0, 2, and 7. So as we work our way through, is this a function or a relation? Well, in order to answer that, we look at the inputs. We have an input of -5 and 0 for its output, input of 0, output 0, input of 5, output of 2, input of 5, output of -7. And really the question we have to ask is, do any of the input values repeat themselves? And in this case the answer is yes. We have this 5 and then another 5. There's not a problem with data repeating itself, it's does it go to the same output? And because the first 5 goes to 2, the second 5 goes to a -7, the answer here is no. This is not a function, but it is just a relation. Looking at our second set of points, -4, -1, 2, and 5 are our input values, and each one is unique. So since they are unique, the output values really don't matter, and we can say yes, this is a function. Next, from a table of values perspective, our x's are listed as our inputs, our y's are listed as our outputs. And again, do any of the input values repeat themselves? Since we have 2, 4, and 6, each one being unique, we would have to conclude that yes, this is a function. Now going to our last, the mapping diagram, the items on the left are input values, or what we're starting with. The values on the right are our outputs. And the way the arrows work is they connect an input value to an output value. So this would be the equivalent of having the point 1, 5. Then we have the point 2, 6, and the point 1, 9. So do any of the input values lead to multiple output values? And here the answer is yes, they do. 1 goes to 5 and 1 goes to 9. So if I were to ask or provide the input value of 1 and ask what is the output value, there would have to be some discussion, because sometimes it's 5, sometimes it's 9. Because that discussion would happen, no, this is not a function, it is merely a relation. This is how we can see it with points, tables, and mapping diagrams, but what does it look like from a graphical perspective? Let's take a look. Here I have several different graphs that show connections between these values. Now in a graph, the horizontal direction is called x and the vertical is y. The main lines that you see with the arrows on the end, these are the axes of the graph, and at the center where the two axes meet is called the origin, the point 0, 0. So as I look through, does it appear that any input value, any x, has multiple output values? Well, at this input value of x, I have a single y. At this input value of x, again I have a single y. At this input of x, I have two different output values of y. And here, single x, single y. Because I have two outputs on this one input, I would have to conclude, no, this is not a function, but merely a relation. Our next graph, as we move across our graph from left to right, for any location that I have my graph showing up, there is only one specific y value that comes into play. So I would say yes, this is a function. Moving to our next one, again, for any x value location, how many y's do I get? 1, 1, 1, 1, 1, and 1. Each x has only a single y located, so yes, this would be a function. And then coming to our last graph, at any given x value, it's appearing as if I have two y values. So because that happens, I would have to conclude, no, this is not a function, but merely a relation. Now in these graphs we have a couple of other characteristics. The graph numbers 1 and 3 are what we call discrete graphs. They're individual dots of data points. Nothing connects them. At graph numbers 2 and 4, these are called continuous, where we started a point or started a value and it is connected and everything in between, not just the numbers that are shown on the graph, show up. So if we were to do a coordinate system, this here has an x value of 1, and then we jump ahead to an x value of 4. Nothing occurs between 1 and 4. Whereas in our second graph, at x equals 1 and then x equals 4, not only do we have values at those locations, but we have everything in between. So discrete are individual dots, and continuous are long connected lines or curves. But what we're focusing on in this slide is what's called the vertical line test. Now to define this, a vertical line test is a graph as a function when no vertical line passes through more than one point on any given x value. So on each of these I went to a specific x or any x and found, do I have one point only or do I have multiple points? For the ones that gave me 1 point only, such as graphs 2 and 3, each x gave me only one y. Those were functions. For graphs 1 and 4, I had at least one location where for a given x value I had multiple y values, and no, these were not functions, they were only relations. Let's look at another aspect of our functions now. And this is going to be domain and range. So let's start out by defining these. Domain is simply the set of all possible input values. Now, not everything has to be included in a domain. Again, for our discrete functions, and that was graphs 1 and 3, our domain was specific x numbers. For continuous functions, it is everything from a beginning point to an end point, and we would have to indicate some sort of arrow system if it were to go on. Now, our range is the set of all resulting output values. So for specific x's, I get specific y's, and that correlates my domain and range. So trying to squeeze this in here, in our first graph, if we use specific points and a scale of 1, our domain values would be the set of numbers -2, 1, 4, and 7. Then from that, our range would be the set of numbers -2, -1, 1, and 3. And how did I occur by those? Again, domain, what x's do I have dots showing up on? And range, what y's do they come out on? So, for a discrete graph, such as number 1, this would be how we can list out our domain and range, as sets of numbers. The braces on the side meaning set. Now, for a continuous function, our domain would be everything in between. So, for the first graph, if I take just what I see, my domain would be x is, or -5 is less than or equal to x, which is less than or equal to 7. If we were to assume that this continued on forever, my domain would be -infinity is less than or equal to x less than or equal to infinity, also known as all real numbers. Now my range, from what I see on this graph, comes out to be from -7 being less than or equal to y, less than or equal to +7. Again, if we were to continue this out, we would assume that it goes from -infinity to +infinity. Our third one, again a discrete function, so I'll list out individual points. My domain is the values -6, -3, -1, 1, 4, and 6. And then the resulting range is -2, 1, and 5. Our last graph, our domain, as what's seen on the graph, takes us from the far left-hand side at x values of -7 and ends at almost the far right-hand side at x value of +6, and we're including everything in between. Our range comes out to include everything from -5 being less than or equal to y, which is less than or equal to 7. So we can write these in set notation for discrete points or as compound inequalities in regards to continuous functions. Now, a lot of items going on so far with our functions. Do have one more topic to cover, and that is types of variables. So when we look at variables of functions, we have independent variables and dependent variables. And like the words themselves indicate, independent variables can loosely be defined as the variable or data set that influences what is happening in the relation. So one of them influences the other. For instance, if I'm talking about going on a trip and I have a specific speed, the amount of time that I'm out controls how far I go. So time is my independent and distance is my dependent. If I'm working and trying to earn money, the amount of hours I work influences how much money is earned. So what is in control is my independent variable. And conversely, my dependent variable would be the variable or data set that is being influenced. So as we look through and work with all these different items, what's in control? Independent. What's being controlled is dependent. Now, have a situation here, an equation given, y equals -1/8 x plus 3 1/10. Models the miles remaining, that's the y, in a race after x minutes. You're to identify the independent and dependent variables first. So in this, what is in control? looking at our situation, we have miles remaining based on X minutes of running, or X minutes in the race. So from that description and what our definitions are above, our independent variable would be the minutes in the race. Our dependent would be the miles remaining. So again, just circling these, my independent variable would be the X minutes in the race, and my dependent variable would be my miles remaining, or Y. And that is going to be typical. X is the independent, Y is the dependent. Next, we are told if we use domain values, specifically 0, 5, 9, and 12, what would be the corresponding range values? Now, a race, the time aspect, is continuous. Once you start a race, you are in it until you are finished. Every moment of time in between counts. But you can't really build tables of values or coordinate sets based on that level of interaction. So we select some specific values and see what those result at. A nice way to organize this is with a table. So if I make X and Y, I put in my domain values 0, 5, 9, and 12, and then simply run the numbers through. For instance, if I have negative 1/8 times 0 plus 3 and 1/10, the result is 3 and 1/10. If I were to then go through and say negative 1/8 times 5 and add that to my 3 and 1/10, I come out with a range value of 2 and 475 thousandths. Now I did have fractions and decimals here. I'm choosing to result out in the decimals. Next, if I go negative 1/8 times 9 for my domain value plus the 3 and 1/10, I come out with 1 and 975 thousandths for my remaining distance, my range. And then if I do the same for 12, negative 1/8 times 12 plus 3 and 1/10, I have a result of 1 and 6/10 miles remaining. So we can have a lot going on and a lot of different ways of displaying functions, as well as a lot of different ways of describing them and characteristics for them. Make sure you have all this vocabulary down and ready to use it, because as we study functions, we will keep coming back to them as descriptors and items of use.